Okay, so on this assignment, so if you look on number 1, it says a solid disk. So you've got to go to your equation sheet, either the equation sheet that I gave you or page 210 in your book. That's what I have up here at the first line. Either the equations or look in your book on page 210 to find a particular moment of inertia. Moment of inertia, solid cylinder, 1/2 mr squared. Boom, there you go. On number 2, it has a hollow cylinder, same mass. So number 2, you're going to use 1/2 mr1 squared plus r2 squared. So it's going to be a situation like the Lord of the Rings. That's why I gave you the 2 different radii, 0.09 and 0.1. When you look at that, that is not R1 plus R2 quantity squared. It's R1 squared plus R2 squared. Pay attention to the significant digits. On every number that I gave you here, you have 3 significant digits. When you get to number 5, solid cylinder, you're going to go back to 1/2 mr squared. You're going to apply a tangential force of 8 newtons. You're going to find the moment of inertia, torque, angular acceleration. Are you going to use F equals ma on number 5?
No.
Absolutely not, because I'm making this thing spin. When you get to number 14, let me kind of give you this visual. So you have something like a ping pong ball that's spinning, okay? So I gave you the moment of inertia for a hollow sphere, 2/3 mr squared. You don't have to look it up, I gave you that. It's spinning at 30 revolutions per minute. What are you going to do with the revolutions per minute? Change that into
Radians.
per second. That's going to get you your omega. Mass of the sphere is 24 grams, has a radius of 3 centimeters, determine the angular momentum of the sphere. So in number 14, you're going to use L equals I omega, neither one of which I gave you. You have to calculate the moment of inertia and you have to calculate omega. So that's going to get you the L of the sphere as it's spinning. So imagine it's like a ping pong ball going around like this, okay? Now, at that point, a bug is going to land on the outside of the sphere, and it's going to be spinning with the sphere. So, angular momentum, like we proved, has to be conserved. So, if I look at the L of the ball plus the L of the bug before, has to equal the new L of the ball plus the new L of the bug. Now, did the bug have any initial angular momentum? No, wasn't part of the system. So that's going to be 0. This is what you found on number 14. Okay? You found that number. You don't have to recalculate it. You know the initial angular momentum of the ball. Now, the bug is going to land on the ball. Do you think they're going to spin at the same rate?
Yes.
Yes, because now it's like a California problem, because now they're going to be spinning together. So this is where it kind of sounds like Halloween. So this is going to be the I of the ball times the new omega of the ball plus the I of the bug times the new omega of the bug. But what do you know about those 2 omegas?
They're the same as.
They're the same, so what can you do?
Factor it down.
Factor it out, just like you did before, because it's like a California problem. So this is going to be the I of the ball plus the I of the bug times omega prime. What you're searching for is omega prime. I'm going to tell you to treat the bug as a point mass. Okay? Point mass, you use mr squared. You're just going to use the radius of the ball because that's where it landed. When you get to 16, you want to calculate the angular momentum of the moon as it orbits the Earth. You're going to treat the moon as a point mass. You're going to use mr squared. As the moon makes 1 revolution, how many radians is it going to move through? 2 pi. How long is it gonna take? 27 days. What are you gonna do with the 27 days?
Seconds.
There you go. Now, when you get to 17, keep in mind this little doodad right there, change in angular momentum equals torque times time. Okay? That's the easiest way to do that. Okay, I'm done.